Hello, everyone. This is Spencer Snolling from Hatch, and I'm glad that you can join us today for our monthly webinar on GPSX topics. I'm also joined today by my colleague Jacob Barkley, who will be demonstrating some of the webinar today and covering some of the more advanced applications that you can do with GPSX. And today we're going to be talking about modeling chemical dosage control and optimization in GPSX. So the idea is we're going to talk in sort of two parts. The first half of the webinar is going to focus on what are all the options that you have in terms of using chemicals in GPSX and understanding how to model them correctly. And then the second half is going to talk more about how to use our more advanced optimizer tools to be able to determine the correct dosage for the situation at hand. So as always, if you have any questions, we'll be here and we're going to stick around at the end of the webinar to answer those live. We ask that you put those questions in the chat, and so that way we can keep an eye on those. We'll let those collect while we're doing our presentation, and then we'll hang around at the very end and answer any questions that people have along the way. All right, let's get started. So I'm going to do a quick introduction and then get into a lot of details about the chemical dosage models. I'm just going to try to cover off all of the most applicable ones, the ones that I see people using most on a regular basis. I also have a short desktop demonstration where I'm going to be talking about how to use the sensitivity analyzer to be able to pick the most optimal dosage that you may have for a given situation. And then I'm going to hand it over to Jacob. Jacob is going to talk about how we can use an external optimizer tool in Python to be able to optimize multi-point chemical dosage. And then he also has a desktop simulation that he is going to run live as well. And as I mentioned, we will answer any questions that you have at the end of the webinar. All right, so GPSX actually is used quite frequently to estimate chemical dosage, appropriate levels of chemical dosage for the activated sludge process, and also to sort of optimize that, to do analysis to understand what it's going to be like and what are different different dosing strategies that you might want to use. So the most common chemicals that we see that we have created models for are ferric chloride and alum for doing soluble phosphorus removal, acid and base dosage for doing pH control, and then also carbon, supplemental carbon dosage for denitrification, and lastly, polymer dosage for, well, dewatering and coagulation, and then a few other things here and there. So I'm going to give you some examples and talk a little bit about where you're going to find all of these in GPSX. You'll note right away that I'm going to be showing you a lot of different unit process objects as you're used to seeing them on the drawing board. Each one of these has a little bit of a different usage, and so I'm going to go through those in detail. So you're going to see kind of a bit of a tour around through all the different objects in GPSX that are relevant to chemical dosage. So the nice thing about all of this is once you've set it up and you've got the chemicals going in and you're able to use the models to predict the level of performance that you're going to get out of a certain amount of dosage, we also then are estimating the cost associated with doing that and all of the other side effects, like what does that chemical dosage, what effect does it have on the pH and what effect does it have on the operating cost, right? We accumulate the amount of dollars that are spent by calculating the cost of that dosage too. So by combining all those different kinds of predictions together and using some more advanced tools, you can actually weigh those things one against another and find that right balance between having the right kind of treatment, process stability, getting good treatment and being able to meet your effluent criteria, and also having a good estimate of how much it costs to do that and what is the complexity of the control system that you have. And so you can sort of that balance the performance versus the operations management and cost. Okay, so I'm going to run through a whole lot of different things here in short order, and these are designed to sort of show you where you can find all of the options that you have. As you know, GPSX has a lot of different unit process objects, and we have a lot of menus, so I'm going to take you through a tour of where to find all the good stuff. Okay, there are three basic, specific places where you're going to find most of the chemical dosage options in GPSX. And one of them is in the influent panel. So when you first start GPSX, the influent panel is open at the top. And this is where you would go and get the influent object and drag it onto the board, that one that's showing at the top here. These four at the bottom here are actually all chemical dosage units as well. So COD chemical dosage, this is your supplemental carbon, acid and base and nutrient dosage. These are all ones that you can drag onto the drawing board from here. So that's one place that you'll find it. Second place is this specific object in the primary treatment panel. So that's a couple panels below in the GPSX unit process table. And this chemical dosage object is probably the most commonly used one for all chemicals. It is the inline chemical dosage, and they are very specifically for doing phosphorus removal. And then we have all of these other places. I kind of lumped them together and called them the third spot. All of these objects that I'm showing you on the drawing board right now have a chemical dosage that is actually built into the object itself. So unlike the two that I just showed you, in this case, you won't actually see anything on the drawing board that represents the chemical dosage. It's kind of built into the object itself. So in many cases here, what we're talking about is polymer addition to be able to coagulate and concentrate solids in one way or another. So these ones here, I'm not going to talk about to any great deal today, but you can find a lot more about them in other webinars. And I'm going to give a shout out here to the one that I did on the DAF unit back in the early summer. That also in there, I'm describing how we do the chemical dosage for polymer there to help increase and concentrate those solids and float them out of that unit. Okay, so I'm going to focus mostly on these chemical ones that are in the influent panel and then that inline chemical dosage. So let's start with the supplemental carbon. This is the COD chemical dosage unit. And as you can see here, the first step in the process is after you've dragged and dropped that on your drawing board is to pick which kind of chemical that you have. It's at the top of the menu there, and you can see that we have lots of different options for things that you can do up at the top here. And so we have many different kinds of chemical dosage. Mostly you're probably doing either methanol or this one at the bottom here, mixed substrate. This is the one that you should be using if you have like a synthetic carbon product like micro C or something that you're adding to be able to do denitrification. Now, the way it works is once you've selected that and you select the strength and all of the other details, you are then going to, in the background, what the model does is it actually sets all of the state variables for this particular stream to 0 with the exception of the thing that you are dosing. So in this case, I've got methanol shown here that I selected at the top. And here, this is just plotting all of the concentrations. You see everything is 0 except for the methanol state variable. And in the case where we're doing the one for the mixed substrate, it is actually going to go all into readily biodegradable soluble substrate. Now, I'll give you a little bit of a suggestion here. You can actually combine that object in many different ways and put it into different parts of your drawing board layout. It's a stream like any other stream that you have on the drawing board, so you can put it through a combiner or do whatever you want to do. But this particular object, the dual inlet plug flow tank, is actually the one that's kind of designed to accept the carbon dosage in a nice and easy way. So normally the influent that you've got coming from upstream, so this would be, for example, you're coming out of your primary clarifiers, and the RAS is coming into this lower connection point. It's this upper one that we added here is primarily there to do the COD dosage, to accept the dosage of carbon for your system. And the way that you can control and figure out where that's supposed to go amongst those 4 reactors that are showing there is to open up the plug flow tank operational menu and slide all the way down to the bottom and find the flow distribution panel. This is the one that contains the settings that allow you to do step feeding. It is also the one that allows you to specify where that other upper connection point goes. So if I click on that, you can see here that you've got these influent fractions here. This is the main one, the regular influent for the wastewater. This one here is for the chemical dosage, right? And then this recycle fraction is actually where the RAS coming back. So what you want to do is change this here. These are fractions. You can actually pull down and set this to % if you like. So right now, this is showing that it'll all go into the very front tank, which is possibly where you would want to do that if you were doing, say, an MLE process. But say you were doing a 4-stage Barton flow, maybe I want to have some of that carbon go into the 3rd reactor, then I would change up these settings here to have something here that allowed that to happen. Okay. So what it does is it's kind of like just like doing the step feeding of the influent, and except it's influent number 2, and you can get it to go wherever you need it to go. Okay, moving on to the green one, which is the nutrient dosage. Now, this is nutrient as in both the nitrogen and the phosphorus dosage. This would be like in an industrial wastewater where you're nutrient limited and you want to be able to dose some nitrogen of some form or some phosphorus. And so you can see right here that all these chemicals that you can choose from are all different, but they're all there to basically supply nutrients in one way or another. We also have very much the same thing here for acid and base or alkali dosage. And you can see here we have hydrochloric acid and sulfuric acid and so on. And here we've got various forms of base that we might be adding, sodium hydroxide and so on. Here you can, the idea behind all of these is that you're going to be dosing one or the other that goes into the stream, and then your pH is going to go up or down accordingly. Now, all of these objects actually are the beginning of a flow coming into a plant. That's why they work exactly like an influent object. So not only do you have to specify all of the concentrations, as I was just showing you, basically you will need to specify the flow as well. So you go to the flow menu, flow rate setup, and then you can specify that flow there, here. So I'm showing an example of 85 gallons per day of whatever chemical it is that we're adding there. Now, there's actually a lot of other controller type options available here, and I'm going to come back in about 10 minutes to talk about what those are like as well. Okay, so that's all of the ones that you're going to find in the influent. Those are there to do those particular jobs. Now, this one is actually called the inline chemical dosage object, and it is there specifically for the dosage of iron products or aluminum to do soluble phosphorus removal. So the idea here is you've got these 4 or 5 chemicals that you can do. So there's alum, there's polyaluminum chloride, there's ferric chloride, ferric sulfate. You pick whatever chemical it is you want, and then you can do this either on a mass base or a concentration based focus. So note that this object is not one where you specify the flow. This is an object where flow comes into it and then goes out of it. So this is why we called it inline chemical dosage. So it is basically dosing some amount of solids into this amount of flow that goes through it. And that's why you can choose one of these two ways to do it. You can either say, I'm going to dose a certain kilograms per day or certain tons per day of a chemical, and then we'll figure out what concentration comes out of that. Or you can do it on concentration base where they basically say, I want to dose enough to be able to get to a specific concentration of, say, aluminum in this case, to be able to get that in the flow that's coming through. So we look at the amount of flow that's going through and we figure out what mass is required to hit that concentration that you have specified. Okay, so this object assumes basically that all reactions happen instantaneously and to completion. There is basically no residual reactions that happen in downstream as it goes along. Like we're assuming that, like most chemical reactions, and is that this happens very quickly. So the dosage basically also removes, in addition to phosphorus, colloidal COD, soluble inert COD, and soluble organic nitrogen. And of course, because things like alum and ferric chloride are acids, basically phosphorus removal is going to affect the pH in and of itself, and it is also pH dependent. So we're forming a precipitate that also helps to remove that phosphorus. And in doing that, solubility of that precipitate is a function of pH. So the dosing of it affects its own, efficiency in removing those things. Okay, so that's how you set it up. Now, how do I calibrate this? You can open up this thing called the flocculation and P precipitation parameters menu, and that allows you to sort of adjust some of these parameters here with respect to stoichiometry and efficiency of dosing. So particularly, this is the one that you probably care about the most, which is the PKSP value, the apparent log, negative log of the solubility product. So this is a parameter that you can use to basically turn up or down the efficiency of the removal, right? So it is essentially adjusting the solubility of this thing. Now, this is a very sensitive parameter. So if you're going to use it, you may find that just going from like 13.6 to 13.8 makes a huge difference. That's because it is, of course, a log value. And so So I do note that sometimes I will come in here for projects that I'm doing if I find that something is not matching very well. But usually I don't have to change this one a great deal to kind of dial it into to what I'm looking for. So in addition to that, we also have, whoops, some other parameters here. These are the ones that are for the other materials other than the phosphorus. And so it's very rare that I find that I have to come in and adjust these, but I will let you know that you can make those changes. They're kind of values that are relative to each other. So for example, if I were finding that I wasn't matching the amount of colloids being removed, colloidal COD being removed, I could take this 0.5 value, could set it to 0, so then it won't remove anything at all, or I could increase it with respect to the 0.5 of the other ones, or decrease the other ones. That will allow us to sort of dial in the COD and nitrogen removal here as well. Now, to be honest, it's not really removing a lot. It has a big preference to remove the phosphorus, so most of it kind of goes there. Right. Okay. So these precipitation reactions that are the ones that we have assumed have happened, they actually are also happening in the Mantis 2 biological model. And they take place in any object that has biological reactions. And in fact, you can see them happening in the bioreactors too. So if you go to the output variables menu and you go to the Mantis 2 rates menu and slide partway down, you can find the precipitation reactions there and see how fast and what their relative magnitudes are with each other. So this is how we precipitate struvite in the digester, for example. Now, this is not the same as doing chemical dosage, but since it's relevant to chemical dosage, because these are reversible reactions, so you can actually have dissolution of the solids back into phosphorus again. Those things can happen there as well. Now, you'll find that those things are happening in any one of the objects, any one of the brown objects like this, that these are the ones that have biological reactions, including our digester. Okay, so that's a description of where you're going to find a lot of those chemical dosage units. And I'm going to do a quick demo here just to show you how things look when you use the inline chemical dosage object. So let me close this and go to my copy of GPSX. So just to give you a sense of what we're doing here, this is a conventional activated sludge tank. So our influent primary clarifier at plug flow activated sludge unit, then our inline chemical dosage object, and a secondary clarifier with the recycle, and then our effluent. So the idea here is that I'm going to run a steady state simulation, and we'll be able to adjust the amount of chemicals being dosed here, and we will look at how that affects the phosphorus in the effluent. So before we move over, I'll just open up this menu and I'll show you here that I have chosen to dose ferric chloride in this particular case, and I'm doing it on a concentration basis. So right now it's set by default to 0. I'm not dosing anything, but then by increasing the concentration, I will then get some phosphorus removed. Okay, so let's run it once with no dosage, and we should find that it's oops, I'm going to move this down so we can see that clearly. So here we can see the plant's got, TSS of 11 and the ammonia is less than 0.1. We're fully nitrifying. And if I slide down here, there's soluble phosphorus is 7.38. So I think it was 8 coming in, 7.38 going out. We're basically not doing any significant removal. That's really just a little bit of phosphorus being taken up as a nutrient by the biomass. Okay, so right now, this is the chemical dosage up here. If I increase this, so let's move it up to, let's say 3.5. I'm going to stick that in, and 3.5 milligrams per liter of iron, and then I'm going to run that again, and then we can see, running it to steady state, that what was previously 7.4 is now down to 3.5, 3.6 milligrams per liter. So that's moving in the right direction. We're not all the way there yet. So I'm going to move this now up to 10. And I'm going to do it again. Solve for steady state again. Now we can see that it has dropped all the way down from 3.5 down to 0.16. So what that is that's now showing we're, removing most of the phosphorus, not quite all of it. And so, these models, of course, are designed such that the efficiency of the next amount of dosage that you are doing is always a little bit less efficient than the one before. So getting down to those lower and lower values, the efficiency of the phosphorus starts to drop off, as it does in reality. And so in those cases, what you'll see is, it takes a lot more to get the next, fraction of a milligram per liter as you go. Okay, so now we're there. Note, though, by the way, that our pH, which was previously just over 7, is now down to 6.5, meaning that now we're dosing enough that the ferric chloride is having an effect on the pH itself. And as I mentioned, that affects the efficiency of the actual removal. And in fact, if I really just go nuts here and push it all the way up to 20 and rerun that, so that's a lot now, we'll look at our soluble orthophosphate and it's back up to 7.4 as if we're not removing anything anymore. And that is, of course, because now the pH is way down here at 3.5. And so that's kind of one of the very interesting aspects of the model. You can find there's sort of not enough, and then there's also too much. And so we want to be able to work and find what that optimized point is in the middle. And one way to do that is a sensitivity analysis. So I'm going to reset the model. And I'm going to reset that here. And we're going to run a steady state analysis across this entire range of dosing to see where that spot somewhere in the middle is the best. So the way we do that is we go to this gear button here, and I'm going to turn on the step analyze mode. That means we're going to run one steady state solution after another, and we're going to step all the way through this range here. So now we're in analyze. Nope, sorry, I need to turn on analyze mode. And then now I'm going to switch to look at this graph instead. This one I am now plotting the pH and the effluent orthophosphate numbers versus chemical dosage. So let's start that up. And so just for those who haven't seen this before, what's happening here is we're running many simulations one after another. So you'll see down here that the model's converging again and again. And up here in this upper panel is whatever the current value is of the chemical dosage. And I've set it so that it goes up by 1 milligram per liter each time. It collects all of the output and it plots it on the graph. It's plotting the things that I've asked it to plot versus the chemical dosage. Normally you would see time down here, but this is a sensitivity analysis. So this is now plotting the effluent phosphorus versus the chemical dosage. Okay, so what are we seeing? Well, it's basically telling us that, well, we had 0 dosage. Our phosphorus was way up here at 7 point something. So that meant that was our starting point. And as we add more chemical, and we move to the right here, we can see that, of course, it comes down. And it does kind of hit a point here, roughly, where it's now saying that's about as low as I'm going to get it at this point. I mean, you can see as it moves along and it moves along, it starts to actually come back up a bit. And then at some point, as we're adding more and more acid here, that it is lowering the pH. It starts here at 7.21, but if I click over here, we're down into the 6s, and as soon as it gets kind of low, below 5, it kind of drops off the table. And at that point, it's moved past the solubility. It's now basically saying it can't form the solids anymore to help remove the phosphorus. So therefore, the phosphorus goes back to being basically the same number we started with. It's now no longer precipitating out anything. So that's a really interesting aspect of this. So we know definitely we don't want to be over here. Now that's quite a lot of dosage. You certainly don't want to be operating down there anyway. But as far as optimization goes, we can see that it kind of comes down here. And basically when you get to this spot, so what's this? This is like, this is saying 9 milligrams per liter. So somewhere there, 9, 9.5, 10, somewhere in that neighborhood. We're not going to get any better performance than that. Any more dosage that we reduce, say all the way over to 15 over here, that's just wasting chemicals, wasting cost. It's not going to improve the performance. So if you wanted to optimize, you'd pick a spot like somewhere here. So that's kind of a nice, easy, straightforward way to use a sensitivity analysis to analyze how your plant is going to respond to chemical dosage, plot the things that you feel are important, and see how they change with dosage, and then you can sort of visually understand what's happening and then pick something that is the appropriate level. So that's kind of doing it the visualized and sensitivity analysis method, and Jacob's going to come along and show us a bit more of an advanced way to do a more sophisticated version of this with 2 dosage points later on. But before we get there, I'm going to go back to my slides again, because I want to wind up this part of the talk with talking about how to set up the chemical dosage controllers, automatic controllers that can change things in order to hit certain set points. And also using the operating cost model. So understanding how to calculate how much a chemical is cost is going to go. And if you have dynamics, it's going to, respond to the dynamics over time. Okay, so the chemical dosage controllers, basically these are where we want to set something up so that it is going to automatically adjust the dosage for us as the dynamics and things change in our simulation. So I mentioned before that if we go to the flow rate setup menu for these chemical dosage that are like an influent, so the carbon dosing, the acid and base dosing, those things here, you can set them up with, by default, a constant flow. So that's the first menu here. It's like a pull-down menu. If you set constant flow, you put this number in, it's just going to be constant. So it's not controlled in any way. However, I can change it to flow paste. So if I change it to flow paste, it's basically going to set the amount of chemical dosage in relation to some other flow rate. So what you would normally do is, and the way that this looks here is that it's set up to be proportional to the influent flow. So now a chemical dosage, of course, is going to be a much smaller number than an influent flow. So likely your fraction number here is going to be very small. But you could say that, as the flow goes up, therefore my loading is going up. So therefore I should probably increase my chemical dosage. So flow-based chemical dosage can be done by specifying the label of the actual stream where you want that to be proportional to. And then lastly is a PID controller. That's one where you're looking at an actual set point. I want to dose enough supplemental carbon in order to meet a certain target. So in this case, we're looking, I believe, at total nitrogen in the effluent. That's probably what this cryptic variable name is. And we want to get it at 6 milligrams per liter. So this is a PID control loop set up just like any other PID control loops that we have in GPSX. And we actually have quite a number of different webinars on how to do that, how to set up PID control loops as you go. So that is for doing the carbon one. It has its own way of setting everything up here. That is because you're actually controlling the amount of flow in this case. So here in the inline chemical dosage object, you're not controlling flow, you're only just controlling the amount of dosing in terms of its concentration. So you would have to set up a separate PID controller here. You could grab this object or put it on the drawing board, specify the details, and say that I want to specify that this dosage will happen at a certain rate in order to hit a certain set point. And so you would set up, use the cryptic variable names and mins and maximums and so on. And actually, as I mentioned, we have a pretty good webinar on how to set up these kinds of process controller, either for the one that I was just showing you for the carbon dosage or for this chemical dosage. Look at the implementing advanced process control on our YouTube channel, and I'll have all the details for you there. Lastly, while talking about that tuning, it is a little tricky because the chemical reactions are very fast with respect to changes in the influent and changes in the biological reactions. So therefore, you have to make sure you don't make your controller too bouncy or too aggressive. So the dosages are often proportional to the plant size. So you may find that your gain has to be a larger number, the gain in the controller, a larger number than depending on what the flow rate is for your plant. And so therefore you may want to adjust the gain and try a couple of things just to make sure that you've got it being, just as you would for building any controller, you always want to make sure it's tuned well. Try some different magnitudes to test the effectiveness of that controller. Okay, and the last thing from me right now will be the chemical dosage operating cost model. So I'm just going to say very few words there. Any object that has chemical dosage will have an associated operating cost model for those chemicals. And you can get at that menu by right-clicking on the object, going to Input Parameters, Operating Cost, and you will be presented with a menu. It may have other things in here related to energy and pumping and other things, but if it has operating costs, you may find you'll find it there somewhere in the menu. And in this particular case, actually, the only operating cost associated with inline chemical dosage is the chemicals themselves. And if you click on this thing, you'll get a menu that looks like this, where it shows you that for this chemical purity, we're looking at this kind of cost for that particular chemical, right? So you'll see here that this is in dollars per kilogram. Depending on what menu or what units you like to work in, you can change this accordingly. So now these numbers are sort of just some rough estimates, and you can change these as needed. So what happens then is we keep track of the total amount mass or volume of the chemical that you are dosing, and then we calculate the cost associated with that. We integrate those dollars over time, and that becomes part of the operating cost summary. Now, if you run a simulation and you get to the end, you can go into this visualization thing, the eyeball button at the top, click on the operating cost summary, and amongst many things, you will get the ability to look at it by object, or for the whole layout, what the various costs are that are associated with this plant. So in this particular example, we can see here that this much of it was 27.4% of it was chemical dosage cost in this particular case. All right, and then one last thing I'll say is that we do have a whole other library for doing water treatment as opposed to wastewater treatment. So our process water library is there for, it works exactly the same way in GPSX, and the process water library is there for doing ultra pure water treatment and drinking water treatment. And so it has an entirely other set of chemicals and other set of unit processes that use chemicals. And therefore, I didn't have time to include any of this stuff in today's webinar. However, we do have an entire webinar about the water process library that I recommend you take a look at our YouTube channel. And on that channel, you can see more descriptions about the various types of chemicals that are there. However, I will say that everything I've told you up until this point is still true for the process water library. It's just that we're dealing with different chemicals. So you can still set them up with controllers, and you can still do those types of sensitivity analysis and so on and on. It all applies there as well. Okay, so what we're going to do now is switch gears. I'm going to hand things over to Jacob, and he is going to talk about doing a more advanced version of what I was showing you with the sensitivity analysis. His plant will be a little bit more complex, and he's going to take advantage of using our Python integration, which allows you to use other optimizers and things outside of GPSX to answer it in a more sophisticated way. So over to you, Jacob.
Thank you, Spencer. All right. As Spencer mentioned, I'm going to take a look at doing Python optimization to do chemical optimization in GPSX. So first, just a little bit of background about why you would actually want to do Python optimization in GPSX. So by including Python into GPSX, you essentially have the ability to expand upon the optimization capabilities that are included in GPSX out of the box. For example, you can use Python to add additional optimization algorithms that may not be included in the base version of GPSX, where those can be your own optimization algorithms where you've written that Python code, or you can take advantage of the wealth of open source Python libraries that are available to you with Python. It also adds the flexibility to define custom objective functions inside of Python, so you have a little bit more flexibility how you set that objective function. You don't have to rely on just using Axel code, for example. It allows you to do multi-objective optimization if that's something you're interested in. And it also adds the ability to add more detailed constraints to your optimization problem. You're not just limited to setting the bounds of your manipulated variables as constraints, for example. It's important to note also that Python is included as part of the GPSX Pro Plus license. So if you'd like to use Python in GPSX, you will need to get one of those Pro Plus license. All right, so for anyone who's never seen our Python functionality in GPSX, you can access it through what we call the Python Script Manager. That handles all of the Python functionality that we have in GPSX. And the Python Script Manager is only available when you're in simulation mode. And to get to that Python Script Manager, you go to Tools on the main GPSX toolbar. It'll have a drop-down, and then there's that Python Script Manager option that you can select. I'm not going to go into all the details about the Python Script Manager, but we do have several webinars that we've done in the past that are focused very specifically on Python and GPSX. I'd highly recommend you go check out our Connecting GPSX and Python for advanced simulation analysis if you want more of an insight and more detailed look at how Python's used in GPSX. All right, so let's get into the actual optimization problem that we'd like to use Python for. So we're going to take a look at a very simple, basic conventional activated sludge system where we want to do chemical phosphorus removal. So in this process, we have an influent, we have our primary ferric chloride dosage point, we have a primary clarifier, an aeration tank, a secondary ferric chloride dosage point, our secondary clarifier, and then an effluent. So it's just a very basic process. What we'd like to do is we'd like to leverage Python to perform an optimization to give us the best values for our primary and secondary ferric chloride dosages so that we meet a couple of effluent phosphorus targets that we're going to set while minimizing the caustic chemical that it requires to meet those effluent phosphorus targets. So the Python library that we're going to be using in this particular example is called PyMu, and that stands for Multi-Objective Optimization in Python Library. And PyMu is a Python optimization library that's focused on single and multi-objective optimization. So they have a whole bunch of algorithms that are included in it out of the box. So they have things like genetic algorithms, differential evolution, Nelder-Mead, NGSA2, MOED, and a whole bunch of other algorithms if you're interested in those. But we're going to focus specifically on using the genetic algorithm in the example that we're going to work through. So for anyone who's not familiar with the genetic algorithm for optimization, this flowchart basically summarizes what that optimization algorithm looks like. So you start by defining an initial population, where that's going to get characteristics of your of the manipulated variables through your optimization problem. So you set your bounds for the manipulated variables, and it's going to create a population of individuals that have randomly selected values between those manipulated variable bounds. Then you'll assess the fitness of each one of those individuals. So you'll find what the objective function value is for that unique combination of manipulated variables to get a fitness value. Then you'll perform the selection step where you compare the fitness of each one of the individuals and identify which are the fittest individuals that you want to continue to look at and generate a new population with. Next is the crossover step where you take that selection of fittest individuals and essentially mate them together. So you create a brand new population of offspring where they have characteristics that are shared between their parents that were mated together. So you get a little bit of, they'll essentially combine the manipulated variables from one parent and take half of those and combine them with half of the other manipulated variable settings from the other parent. Then finally, we have a mutation step, where that's essentially a way to introduce randomness into our optimization algorithm with a predefined probability. So when that probability is met, we'll perform mutation, which is essentially it takes one of your manipulated variables and assigns a random value to that, so that you can explore other regions of your optimization zone that maybe your parents' fitnesses only focus on one section, but by introducing randomness, we'll look elsewhere, and that might get us out of, say, for example, a local minima and push us towards finding the global minima instead of the local one. After all these steps, you check to see if your algorithm has converged and you're at your termination criteria. If it hasn't, you'll repeat all of these steps over and over again until you do reach your termination criteria, and then you can exit out of the algorithm, and you'll get what the best results are. So traditionally, an optimization problem is defined like this. So we say we want to minimize some function, f of x, where it's always set up as a minimization. So if you want to maximize something, for example, you'll just have to multiply your function by -1 so that you're doing a minimization. Then you apply a couple of mathematical formula to that function. So you subject it to inequality constraints, where those are going to be some variable is less than some value targets. You can apply equality constraints where you say some variable has to be equal to some value. And then finally, you have your manipulated variables, where you set a collection of manipulated variables that you want the optimization algorithm to change, and you constrain it between a lower bound and an upper bound. Then the optimization algorithm will select values from that to find what the solution is. So let's actually format our ferric chloride dosage problem in terms of an optimization definition. So first, we'll define our objective function, where what we're interested in doing is minimizing the cost of our ferric dosing. So we're going to add up our primary ferric cost and our secondary ferric cost, and we want to minimize that value so that we have as low a cost as possible while meeting our constraints. So next, we'll define our inequality constraints. And we're interested in 3 constraints. First, we're going to say that our total ferric chloride dosage has to be less than 400 kilograms per day. Next, we'll say that our effluent total phosphorus has to be less than 1 milligram per liter. And finally, we'll say our effluent orthophosphorus has to be less than 0.5 milligrams per liter. We aren't interested in adding any equality constraints in this particular optimization problem, but we will add our manipulated variable definitions next. So we're going to have 2 manipulated variables. We'll have our primary ferric chloride dosage rate, where we're going to bound that between 0 and 400 kilograms per day. And then likewise, we'll have our secondary ferric chloride dosage rate, where that is also bound between 0 and 400 kilograms per day. All right, next, let's take a quick look at how this could be implemented in Python to then drive a GPSX simulation to do this optimization. So I'm just going to step through some code, and then we'll actually run this code in the demonstration a little bit later. But just so you're familiar with what it's doing, first we need to specify what our manipulated variables are going to be. So we're going to specify that we're manipulating the primary ferric dosage rate and the secondary ferric dosage rate. Where you can see in this first Python variable definition, we have the cryptic tags that correspond to the GPSX cryptic tags, and that's what we're going to be changing. And we specify what our lower and upper bounds are going to be. After that, we then define a function that is going to correspond to our objective function. So we use the GPSX get value function to get values from GPSX and have those be pulled into Python. And what we're going to use for our objective function is we're going to sum up the cost per day of primary ferric dosage with the cost per day of secondary ferric dosage. Next, we have to define our constraints. So we have our 3 constraint functions where we're going to get the value of the total ferric chloride consumption per day and say that has to be less than 400 kilograms per day. We have a constraint for our total phosphorus in the effluent, and we're saying that has to be less than 1 milligram per liter. We have a constraint for our ortho P in the effluent stream, and we're saying that has to be less than 0.5 milligrams per liter. Next, we actually have a function call to the run optimization function that we'll step into and take a little bit of a look at in a few slides. But what this is going to do is it's going to actually be responsible for running the optimization in Python. After that's run, we get a results variable, and we're going to just parse that results variable to print out our results so we can see what the optimization did, what it found as the optimized value, and just have that displayed to us in a nice readable fashion. So if we take a look at that run optimization function, you can see here, what we're doing is we're defining a optimization problem class. That just provides to PyMu the kind of definition of what our optimization problem is going to be. So it says how many manipulated variables we have, how many objective functions, how many constraints, and then what the bounds that it can work with for those manipulated variables are. We also have a evaluate function that you can see here, where this is what the Python is going to actually use to see what the performance of a particular individual in our optimization function was. So we call the optimization iteration function, where that's going to actually perform an iteration of the optimization so that we can see how that simulation worked. And then it's going to take that to get the results. So it's going to output the objective function value, and it's going to output the constraint values, and then store those so that Python can see them, and it can essentially use that as insight to how that individual performs, so it can look at the fitness and see if it actually met all of our constraint values. So if we take a look at that optimization iteration function quickly, you can see this is where we're actually calling the GPSX simulation. So we call GPSX reset sim so that each one of these individuals are essentially independent. So we reset the simulation, we set our stop time to 0, and we set steady state to true. So we're going to run a 0-day steady state simulation. So each one of those individuals is going to have to find steady state before we get results from it. Then we set the manipulated variables that the optimization algorithm is providing to us, and those are set with the GPSX set value command. And those will be, so essentially it's going to change what our ferric chloride dosage is for each one of these individuals when they're being executed. Then we call our run sim, and it will actually execute the GPSX simulation and then pull those results out after. All right, and then the last little bit of code is just setting up the PyMu functions so that they can actually run our optimization. So we define what our algorithm is going to be. And you can see we're defining a genetic algorithm with a few characteristics where those might be things that you tune or you know, or you're just exploring to get your best optimization. We define what our termination criteria is going to be. Then finally, we call the minimization function, where that's going to actually do the PyMu minimization and provide our results to the res variable, return that, and then we're going to print them out so we can take a look at them later. So with that background, now let's actually take a look at a desktop demonstration of how you can use Python to perform a optimization in GPSX. So if I switch over to Python, which you can see here, you can see what we're doing is we have our conventional activated sludge plant that I showed you earlier, where we have our influent, we have our 2 ferric chloride dosage points, our 2 sets of clarifiers, and our aeration tank. If we take a look at our primary ferric chloride dosage point and we go into our chemical dosage settings, you can see we're dosing ferric chloride, and it's going to be a mass-based dosage. So we're going to specify how many kilograms per day we're dosing instead of a concentration of ferric that we want to maintain. Likewise, for our secondary, you can see we are also dosing ferric chloride, and it is also mass-based. So now if we move into simulation mode, you can see our layout, and we can do just some a little bit of exploration to see how our plant's performing without any ferric chloride dosing. So if we run the simulation, we can see that we have 8 milligrams per liter of soluble phosphorus coming in and 10 milligrams per liter of total phosphorus. We take a look at our input sliders. We can see that we are not dosing any ferric chloride. So this is the slider for the primary and the secondary. Both of those are currently set to 0 kilograms per day. And if we move over to this output tab, we can see a little bit more details of how our simulator is performing right now. So we're not consuming any ferric chloride because our dosages are set to 0. Likewise, our cost is 0 since we aren't dosing anything. Then you can see what our effluent phosphorus is. So our ortho P leaving is down to 7.375. So that's just removing a little bit through the biological process since we aren't doing any chemical phosphorus removal. Likewise, you can see our effluent total phosphorus is reduced a little bit to 7.783. Then here we just have a visualization of how phosphorus is leaving, how phosphorus is changing through the system. So this first bar represents the phosphorus that we have coming in, where the first plot corresponds to ortho P and the second plot is total phosphorus. The second bar corresponds to the phosphorus concentrations that are leaving the primary clarifier overflow. Then our final bar shows what the effluent concentration is going to be. So that's what's leaving in the secondary clarifier overflow stream. We could try doing a manual optimization to try and get our best performance. We could do that by, say, increasing. So we're dosing all our available ferric chloride to our primary dosage point. And see, that does do a good job of removing phosphorus now. So our ortho P is down to 0.14. Our total phosphorus is down to about 0.8. But we are dosing 400 kilograms per day, and it's costing us $304 per day. We could explore other options. For example, we could dose everything to our secondary ferric chloride dosage point. If we do that, you can see our total phosphorus actually increased, but our ortho P did go down from the primary ferric chloride dosage point. We're still dosing the same amount, and our cost is still the same as when we were dosing everything to our primary point. Or we could try doing some sort of optimization for our dual point dosage by saying, let's split it down the middle and have 200 kilograms per day going to both points. If we run that, you can see that we're doing a little bit better on the ortho P than we are doing with the primary dosage. And likewise with the total phosphorus, it's a bit better than when we were doing secondary dosage. But we are pretty far below our targets. For example, we could have more total phosphorus coming out and we could meet our 1 milligram per liter target. Likewise, we could do that with our ortho P with our 0.5 milligram per liter target. And if we do that, we can kind of fine tune our optimization so we aren't using the full 400 kilograms per day and it's not costing us $304 per day. So that could be done manually, but we're going to take advantage of Python and do an optimization. So I'm going to open the Python script manager. You can see it does have a Python script already added to it. So I did create a Python script that had what we showed in the PowerPoint slide, and it's available for us to use. So if I press run, it's going to start executing that Python script. And what you can see is it's manually changing on its own the ferric chloride dosages as it's exploring the problem. And it's running all of these simulations, which is shown by it repeatedly converging. If we take a look at our outputs, you can see that each one of these simulations is using a different amount of ferric chloride dosage. So that value here, our total ferric chloride consumption, is changing throughout the simulation. Likewise, our ferric chloride cost is changing in response to how much we're dosing. You can see our ortho P and total phosphorus are also changing throughout that simulation depending on how much is being dosed. If you take a look at our plots, you can see these bars aren't always reaching the same value, so it is essentially responding to the different dosages as it simulates. So what the script's doing is it's now trying to find the best set of conditions that will meet our predefined constraints for our ortho P and total phosphorus while minimizing our ferric chloride consumption. And you can see it's terminated. It's run all of its simulations to reach the termination criteria. And if we take a look at a summary, we can see the best solution that it had was dosing 185 kilograms per day to the primary ferric dosage point and 66.1 kilograms per day to the secondary ferric dosage point. This is going to cost us $192 per day. And it's going to result in a total phosphorus in the effluent of 0.98 and a soluble phosphorus in the effluent of 0.187. What we could do is we could then take a look at how this runs in our by manually running it just to compare to make sure that what we got from the optimizer is correct. So if we set those values, so 185.8 for our primary ferric dosage and 66.1 for our secondary ferric dosage, close the Python script manager, and run a manual simulation, you can see we are getting those same results. We're dosing our 251.9 kilograms per day. It's costing us about $192 per day, and we're having these effluent concentrations. It's important to note that when you're doing an optimization, it will tend to try and force one of the constraints to be the condition. So for example, in this case, our total phosphorus, it had 1 milligram per liter as the constraint. So it's going to try and find a solution that pushes that as close as possible to 1 milligram per liter, because that is usually, it'll cost more to lower that further. So it's important to keep in mind when you're saying an optimization, if you have a hard limit for one of your constraints, you might want to set a little bit tighter of a constraint so that you aren't falling directly on that when you perform the optimization. All right, so I'm going to hand it back now to Spencer just to close out the webinar.
Thank you, Jacob. So I'm just going to share a couple of slides just to wind things up. And then if you have any questions, please type those into the chat or the Q&A panel that is available here in Teams, and we'll get to those shortly. So just to kind of wind things up, as we always do, just wanted to mention and summarize that there are a lot of different chemical dosing options that are available to you in GPSX to simulate different kinds of chemicals, and there's a lot of abilities to put automatic control on those. And just like Jacob was showing, there's a lot of our advanced tools can really leverage the value of those predictions that the models are making to be able to do a really good analysis and determine the optimal dosage for the question at hand, being able to figure out how much is enough to do the job, but we also want to minimize the cost. Lastly, as Jacob was also showing, that Python has quite a lot of different open source tools that are available to do different kinds of sensitivity analysis and also process optimization. And so we encourage you to be able to take a look at all of those things that are available out there. I know Jacob had on one of his slides there, for example, that there's 4 or 5 different kinds of optimizers that we could have shown you today. So by connecting GPSX to Python, it gives you the advantage of taking advantage of all of those different tools that have been developed by other people out there.